Lesson 17 is called Inscribed Angles and Quadrilaterals, and in 17.1 we're going to introduce what an inscribed angle is. So up at the top, an inscribed angle is an angle formed by two chords with a common endpoint. So in this picture we have chord AF and chord BF, and they have a common endpoint F. They form an inscribed angle. That would be angle AFB. So also another kind of way of describing an inscribed angle is an angle formed by 3 points on a circle. So you could see point A, point F, and point B are all on the outline of the circle, and together they formed an inscribed angle. Next is the inscribed angle theorem. So the measure of an inscribed angle is half of the measure of its intercepted arc. So in this case, like we said, we have angle AFB, and that's going to be half of the measure of arc AB, which arc AB is that kind of arc that it hits at the end of the circle or the outside of the circle. And then I'm going to add the little arc symbol here. It's just hard, you can't really type it. But so yeah, our theorem says that the measure of the inscribed angle AFB is half of its intercepted arc, which is in this case arc AB. That also means that the arc would be double the size of the angle. Angle is half the arc is double the angle. Okay, so example 1, it says if the measure of angle AFB is 50 degrees, what is the measure of arc AB? Okay, so we know our angle is 50 degrees. That's given to us. That's this angle inside here. So you can set up an equation like based on that formula in the theorem, and it would look something like 50 degrees equals 1/2 times the measure of arc AB, and then you could solve that equation if you wanted to by multiplying both sides by 2. But I think I would prefer if we kind of just were able to recognize that if you are given the angle, to get from the angle to the arc, you multiply by 2. The arc is double the angle. To get from the arc back to the angle, you're going to multiply by 1/2 or divide by 2. So in this case, since we're given the angle, we're just going to take our angle and we're going to double it. So we're going to multiply 50 degrees by 2 to get 100 degrees, and that's going to give us the measure of arc AB. If we were given that the arc was 100 degrees, we would just need to divide it by 2 to get to the angle. So a measure of arc AB, sorry, I was like trying to say 50 at the same time as writing 100, but the measure of arc AB is equal to 100 degrees. And then, like I said, just to summarize, yes, the theorem says that like the inscribed angle is half the measure of the arc. That also means the arc is double the angle. I'm going to add a note of that here. So arc is double the angle. Just so that way you can kind of go both ways. Okay, moving down to the next section. A corollary is a statement that can be made based on a previous statement. So we have a couple corollaries that are based off of that previous theorem. So the first one says the measure of a central angle is twice the measure of any inscribed angle that intercepts the same arc as the central angle. So just to kind of digest this, it says the measure of the central angle. So central angle is angle ACB in this case, is equal to twice, that means 2 times, the measure of any inscribed angle that intercepts the same arc. So the measure of any inscribed angle, that would be angle ADB, that intercepts the same arc, like both of those angles intercept arc AB. And that's based off the previous theorem because earlier, like a few lessons ago, we learned that the central angle in the arc, central angle is like attached to the center of the circle, but the central angle and the arc that it connects to are going to be the same. So those would be like the same measurement, like angle ACB and arc AB, those would be the same. And we know that the arc is double the inscribed angle, that's like angle D that's kind of further away. So it makes sense that the central angle would also be double the inscribed angle. Okay, so corollary number 2. If inscribed angles of a circle intercept the same arc or intersect the endpoints of the same chord, then the angles are congruent. So in this case, we have angle ADB. So this angle right here. And we have angle AEB, which is this angle right here. And they intercept the same arc. That makes them congruent. So if we think of like the arc as how wide the angles are opening up to, like depending on how big the arc is, completely corresponds with like how open the angle is going to be. Like if the angle gets wider, the arc will get wider. So if two angles are like hooked onto the edges of the same arc, they have to be the same size angle for the opening to be the same. Okay, so in this case, angle ADB, the blue angle, is going to be congruent to angle AEB, the purple angle, because they both intercept the same arc. Okay, example 2, find the following angle measures with the measure of angle AEB. So angle AEB is this one right here. That angle intercepts arc AB. And there's another angle in that picture that also intercepts arc AB, and that's angle BDA. So angle BDA intercepts arc AB, and that angle is given to us. It's 61 degrees. The angle that we're asked for, angle AEB, which is kind of like near point E, it intercepts the same arc. So using this corollary number 2, this one up here, that must mean that they're congruent to each other because they open up to the same exact size arc. So their angle openings must be the same. So that would mean that this angle would also be 61 degrees. So the measure of angle AEB is 61 degrees. And then moving on to angle EAD, I'm going to erase some of this. So angle EAD is from here to A to D. And we can see that that opens up to an arc that we can see. So that angle EAD opens up to arc DE. And we're going to go way back up to the theorem for that one. So all the way up here. It says the measure of an inscribed angle is half the measure of its intercepted arc. So in this case, we have an inscribed angle, EAD, and its intercepted arc, which is DE. So it's going to be half of that arc. That arc is 155.6 degrees. We need to find half of that. So it would be 155.6 degrees divided by 2. So 155.6 divided by 2 is 77.8. So this would end up being 77.8 degrees. And that's this little angle inside here. I'm going to write it kind of small in there so we can see it. So this is 77.8 degrees. Okay, so the measure of angle EAD is 77.8. I know I've said that like 5 times now, I'm sorry. And then the next one is the measure of angle AGE. So AGE is we're starting at A, we go to G as our vertice, and then finish off at E. So that's looking for like this angle inside here. And at this point, we have like a triangle. So just kind of close it off this way. We have a triangle and we know 2 out of the 3 angles in that triangle. So as soon as you know 2 out of 3 in a triangle, you can just subtract them from 180 using the triangle sum theorem. So there's always 180 degrees in any triangle. And since we know the 2, we can just subtract them to find the third. So it'd be 180 degrees minus 77.8 degrees and then minus 61 degrees. So we do 180 minus 77.8 and then minus 61. So it ends up being 41.2. So the measure of angle AGE is 41.2 degrees. So angle AEB, that was the one that was like near point E. We found that because it was the same as that other 61-degree angle because they open up to the same arc. And then angle EAD, that was this angle right here, and that opened up to the arc that was 155.6, and the intercepted angle, or sorry, the inscribed angle is going to be half of that arc that it intercepts. And then lastly, we found the measure of angle AGE. And we just found that using the triangle sum theorem because we found out two of the angles of that triangle, so we just subtracted those two angles from 180 to find the third. Okay, moving down to the next theorem, it says if an inscribed angle intercepts, an inscribed angle intercepts a semicircle if and only if the angle is a right triangle. And keep in mind that if a arc is a semicircle, that means that it connects to the diameter. The endpoints are the diameter of the circle. Okay, so example 3, it says in circle C, BE is a diameter and the measure of angle B is 32 degrees. We want to find the measure of angle E. So it's giving us that BE is the diameter, and that means that arc BE is a semicircle. So this is a semicircle, meaning it's like exactly halfway around the circle. And because this theorem is an if and only if, it means it goes both ways. So in this case, we're given that it's inscribed, the angle inscribed intercepts a semicircle. We know that. Because we know that, then we can kind of claim that the angle that forms that, or kind of the inscribed angle, is a right angle. So that would mean that angle D is a right angle, and that means it's 90 degrees. Okay, so the angle that opens up to a semicircle is going to be 90 degrees exactly. And then now all of a sudden we know 2 out of the 3 angles in this triangle. We know the one that's 32 degrees right here. We know the one that's 90 degrees. We just need to find the measure of angle E now using the triangle sum theorem. So we'll do 180 degrees minus 90 degrees, and then minus 32 degrees. If you recognize that 180 minus 90 is 90, you can just do 90 minus 32, that's fine. If not, also totally fine. So 180 minus 90 minus 32 is 58 degrees. So you'd say measure of angle E is 58 degrees. And then just to summarize that really quick, because we were told that segment BE was the diameter, we knew that arc BE was a semicircle, and because arc BE was a semicircle, the angle that was opening up to it, the inscribed angle, is 90 degrees, is a right angle. Moving down to 17.2, it's inscribed quadrilaterals, and we're just going to start off with vocab. So triangle ABC is an inscribed triangle. It's this triangle inside here. Says it is inscribed inside the circle, and the circle is circumscribed around the triangle. So the word inscribed refers to the inside shape. So in this case, triangle ABC is inscribed. Sorry, that keeps being crooked. And then circumscribed refers to the outside shape. So in this case, circle, it doesn't have a center, so it doesn't really have a name, but that circle is circumscribed because it's around the outside of the triangle. Okay, so the next theorem, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So supplementary means that the angles add up to 180 degrees. And in this picture, our opposite angles are angle Z and angle X. So we could say the measure of angle X plus the measure of angle Z is 180 degrees. And then angle Y and angle W are opposite each other, so the measure of angle W and the measure of angle Y will also be 180 degrees if we add them together. For example 1, it says find the measure of angle Z, and for this example, I'm going to use the most recent theorem to find that measure, and then I'm going to backtrack and use some previous theorems to show kind of why exactly it works. So in this problem, we know the measure of angle X is 100 degrees and angle Z is opposite of angle X, and it is a part of a quadrilateral that is inscribed in a circle. So the theorem says if you have a quadrilateral inscribed in a circle, then its opposite angles are supplementary, and that means that angle X and angle Z will add up to 180 if we add them together. So we can take the measure of angle X, that's 100 degrees, and then add it to the measure of angle Z, which is what we're trying to find. And those two added together should be 180 because they are supplementary. And then now you may recognize like, okay, well, the measure of angle Z must be 80 to make this work. If not, or if you have some harder problems or harder numbers to deal with, you can just subtract the other angle, the one we do know. So in this case, the 100 degrees, so we'll subtract 100 from both sides. 100 degrees minus 100 degrees cancels out, and then I bring down the measure of angle Z equals 180 degrees minus 100 degrees, so it leaves us with 80 degrees. So the measure of angle Z equals 80 degrees. Okay, so anytime we have opposite sides or opposite angles within an inscribed quadrilateral, they have to add up to 180. So you can take 180 and subtract the angle that you know to get the remaining angle, in this case 80 degrees. Okay, so the reason why it works, I'm going to erase some of this. So we know that the angle X is 100 degrees, and we just learned that the arc that it intercepts is going to be double the inscribed angle. So if X is 100 degrees, then the arc that it intercepts is going to be 200 degrees because that's double 100. And then in an entire circle, all the arcs will add up to 360 degrees. So if the arc YZW is 200, arc YXW, the one that's in blue now, must be 160. Because that's what you would need to add to 200 to add up to 360. There's 360 degrees in a full circle. And then we know that the intercepted angle is going to be half of the arc that it hits. So angle Z intercepts this arc now that's 160 degrees. So that means that angle Z is going to be half of 160 degrees. Half of 160 degrees is 80 degrees. So that's a little bit more into like the why that it works. I would never really expect you to do all that just to find angle Z because we know that the opposite angles are supplementary. Okay, moving down in the quadrilateral sum theorem, says the sum of the measures of the interior angles in a quadrilateral is 360 degrees. So all four of the like internal angles, the angles that are within the quadrilateral, are going to add up to 360. For example, 2, we want to find the measure of angle R. Okay, so we know that eventually angle P, Q, R, and S will all add up to 360. That's what the quadrilateral sum theorem states. Because angle P, Q, and S all involve X's and R we don't know at all, we actually can't jump straight to the quadrilateral sum theorem because we would have more than one unknown in our one equation, and you can only have like one equation or one unknown per equation, or I guess like per amount of equations. So if you have one unknown, you can have one equation. If you have two unknowns, you have to have two equations. Okay, so but the thing that we do know from the previous theorem is that the opposite angles are supplementary. So our opposite angles are going to add up to 180 degrees. So we do know, or we do have like two expressions for like one for Q and one for S. So we can start there as a way of like solving for X. And then that would let us eventually figure out what angle R is. So angle Q is 5x plus 8. And then angle S is 3x plus 12. And then those two angles added together should be 180 because they're supplementary. And we can like put the degree symbols on there if we want, but it doesn't like make a difference in the problem. We can just also add them at the very end. So I'm going to leave them off. So we have angle Q plus angle S, because those are on opposite sides of each other. added together 180 degrees because they're supplementary. And then now we have an equation that we can solve for x, and eventually we'll be able to use that x to figure out what all the angles should be. Okay, so from here, before we start using like inverse operations to like cancel things out, you want to make sure each side of the equation is simplified. So if you look at the left side, there's a lot of like terms there that we can combine. So like terms are terms that have the same variable and the same exponent. So like the 3x and the 5x, those are like terms. And then the 8 and the 12, those are like terms because they have no x. And so we just we add them together on the same side. You don't do the thing where you like subtract 5x from both sides or anything like that. That would be very wrong. So here, we're just going to combine our 5x and our 3x, and together that would become 5 plus 3 is 8x. And then we combine the 8 and the 12, and again, we're just like adding them together. So 8 plus 12 is 20, so this would become plus 20. And then we bring down the equal sign and bring down the 180. And then now this entire side of the equal sign is simplified, meaning there's no more like terms for me to combine. There's nothing to distribute or anything like that. So now our focus shifts on isolating x, getting it by itself. So you cancel out the things that are being done around it. The 20 is being added to it. I'm going to subtract it from both sides to cancel it out. Bring down my 8x. 20 minus 20, 0, that goes away. 180 minus 20 is 60. And then now we have 8x equals 60. Now I need to get rid of the 8 that's being multiplied by the x. 8 divided by 8 is just 1x. So it leaves us with just our regular x. And then 160 divided by 8 is 20. So we end up with x equals 20. So now that we have our value of x, there's a couple of different ways that we can kind of approach the next portion of the problem to find the measure of angle r. One is by making like a massive equation of all the angles and setting them equal to 360. I was like working on it that way, and then I realized I feel like it made it more confusing than it needed to be, so I'm going to do it a different way than that. I'm just going to go through and figure out what each angle is first. So we know x equals 20. So if I want to find the measure of angle Q, it would be 5 times 20 plus 8. You would need to follow order of operations to simplify. I'm going to make this a little bit smaller. So it'd be 5 times 20 plus 8. So we would multiply 5 and 20, and 5 times 20 is 100, plus 8 would be 108. So the measure of angle Q would be 108, and then we'll kind of do the same thing for like the measure of angle P. So for P, it would be 4.9 times 20 for x plus 0.6. So 4.9 times 20 is 98, and then plus 0.6. 98.6. So we end up with 98.6 degrees for angle P, and then for angle Q, or sorry, for angle S, we need to put that x in for 20 into the 3x. So it'd be 3 times 20 plus 12 for angle S, and then 3 times 20 is 60, and then 60 plus 12 should be 72 degrees. So that ends up being 72 degrees. So now we have 3 of the 4 angles in a quadrilateral, and we know all 4 are supposed to add up to 360. So we can just add all 3 of those angles, add in the 4th angle that we don't know yet, set it equal to 360, and then solve. So the measure of angle Q, that was 108 degrees. The measure of angle P, that was 98.6 degrees. And then the measure of angle S was 72 degrees. And then next we need to put in that 4th angle, which we don't know yet, but we're going to find that's going to be the measure of angle R. And then all 4 of those angles added up together should be 360 degrees. And then now we can add 108. We're just going to add all the numbers on the left side of the equal sign that we can. So it would be 108 plus 98.6 plus 72. Just so we don't have to like subtract them over one by one, you can just add them all together on one side by combining like terms. So it'd be 108 plus 98.6 and then plus 72 equals 278.6 degrees. And then plus whatever the measure of angle R is equals 360 degrees. And then from there, we just want to get the measure of angle R by itself. So I'd cancel out that 278.6 that's being added to it. I just need to subtract it over. So minus 278.6 degrees minus 278.6 degrees. And then these will cancel out. I'll bring down my measure of angle R. And then 360 degrees minus 278 degrees is 81.4 degrees. So we end up with the measure of angle R equals 81.4 degrees. Okay, so just to kind of summarize this last problem, the quadrilateral sum theorem, similar to like the triangle sum theorem, that in a triangle, all the angles add up to 180. In a quadrilateral, all the angles add up to 360. So if you can get to the point where you know 3 out of the 4 angles in a quadrilateral, you need to subtract those 3 from 360, and you'll be left with that final 4th angle. In this problem, we had to do a little bit of work before we could actually find those like first 3 angles. We had to solve for x. We solved for x by like knowing that the opposite angles were supplementary and setting the sum of those opposite angles equal to 180 to solve for x.